If the universe has an edge, no telescope has ever seen it, and it's possible none ever will. Hello, and welcome to Somniora Mind. I'm glad you're here. Tonight we're going somewhere that doesn't quite exist on any map, the outer edge of everything. Not a wall, not a fence, not a place a spacecraft could ever bump into. Something stranger. Somewhere between now and the beginning of time, there is a boundary that light itself has not yet crossed to reach us, and beyond it, we simply do not know what is there. It might be more of the same. It might be something we don't have the physics to imagine yet. Before we drift into that, 3 quiet questions to carry with you tonight. Keep them loose, like something you're not trying to solve, just something you're letting sit in the back of your mind while your body settles. First, if the universe is expanding, what exactly is it expanding into? Second, when you look at the night sky, are you looking at space, or are you looking at time? Third, is it possible that somewhere out there, past everything we can detect, there's a version of the edge that isn't an edge at all, but a place where the rules simply stop applying? We'll return to all 3 before the night is through. You don't need to hold on to them tightly. Just let them float somewhere nearby. Some of what we cover tonight rests on solid, tested science, measurements made with real instruments, numbers confirmed again and again. Other parts sit further out, at the edge of what physics can currently prove, in the territory of educated theory and careful speculation. I'll try to make clear which is which as we go, because I think the honesty of not quite knowing is part of what makes this subject so calming. Nobody has to pretend to have all the answers out here, not even the scientists. If you find these journeys helpful, know that the quiet ways you support this channel, like a moment shared with someone who might need a slow night, means something. They help this reach the next tired mind that needs it. That's really the whole idea. One quiet mind at a time. For now, there's nothing to do but let go of the day. Let your jaw unclench. Let your shoulders drop half an inch further than you thought they could. Let each breath out be a little longer than the breath in. You don't need to keep track of anything I say. You don't need to remember any of this by morning. Just let the facts drift past like something seen from a train window, half lit, half forgotten, moving away from you into the dark. Let's begin at the edge of everything we can see. Every single point in the universe is, technically, the center of its own observable universe. That sounds like it shouldn't be true. Centers are supposed to be special. There's only meant to be one. But cosmology doesn't work that way. And once you sit with the idea for a while, it becomes strangely comforting rather than strange. Here is the quiet reasoning behind it. When astronomers talk about the observable universe, they don't mean the whole universe. They mean the portion of it whose light has had enough time to reach us since the beginning. Light travels fast, but not infinitely fast, and the universe has only existed for a finite stretch of time. A long stretch, but a finite one. That means there's a maximum distance light could have traveled to reach Earth by now. Draw a sphere at that distance, with Earth at the middle, and you have what we call our observable universe. Now here's the part that changes everything. That sphere isn't drawn around some special cosmic landmark. It's drawn around us simply because we are the ones doing the observing. If you were standing on a planet on the far side of that sphere, light would have had exactly the same amount of time to reach you, just from a different direction. You would draw your own sphere, centered on yourself, and it would look just as complete, just as vast, just as edge-lined as ours does from here. So the observable universe isn't a place. It isn't a region carved out of space with fixed borders like a country on a map. It's a relationship between where you are standing and how long light has had to travel toward you. Move the observer, and the sphere moves with them. There is no single true center of the universe that everyone shares. There are only billions upon billions of overlapping circles, each one centered on wherever someone happens to be looking from. It helps to picture the universe as an ocean of fog stretching in every direction, farther than anyone could ever walk. Each person carries their own small lantern. The light from that lantern reaches only so far before it fades into the fog, and that fading edge is different for every person, even though they might be standing quite close to one another. No one's fog edge is more real than anyone else's. No one is standing at the true middle of the ocean, because there isn't one, or if there is, nobody can reach it, and nobody needs to. This is one of the strange comforts hidden inside cosmology. There's an old, human instinct to want to know where the center of things is, the center of a room, the center of a story, the center of importance. But the universe, at its largest scale, offers no such landmark. And instead of that being a loss, most physicists find it to be something close to peace. Nothing is at the edge. Nothing is left out. Every observer, everywhere, gets their own complete horizon, drawn just for them, simply because they exist and are looking outward. There's a second layer to this that's worth sitting with before we move on. Because our observable sphere is centered on us and made of light that has been traveling for a very long time. We're not just looking outward in space. We're also looking backward in time. The farther away something is, the older the light is that we're receiving from it, which means the farther away something is, the further back in cosmic history we're actually watching. Someone on that hypothetical planet on the far side of the universe, looking back toward us, wouldn't see the Earth as it is right now. They would see light that left our region long ago. Light that, if anyone were there to send it, might show a version of this corner of space before our sun had even finished forming. In a very real sense, none of us can see anyone else's present moment. We can only see each other's pasts, stretched out across unimaginable distances, arriving at exactly the moment we happen to be looking. So if you ever feel small against the scale of the universe, you might try holding this thought instead. You are, quite literally, at the exact center of everything you can perceive. Not because you're special in any cosmic sense, but because that's simply how observation works. Every mind looking upward tonight, in every direction, on every world that might exist, is standing at the middle of their own small, complete sphere of stars, each one honest, each one real, and each one, in its own quiet way, whole. The darkness between the stars is, in its own way, one of the strangest puzzles in all of astronomy. It seems almost too simple a question to be scientific. Why is the night sky dark? And yet for centuries, that question quietly troubled some of the best minds in physics. Because if you think it through carefully, the darkness doesn't actually make sense. Imagine, for a moment, that the universe were infinite, unchanging, and evenly filled with stars, stretching outward in every direction without end. If that were true, then no matter which direction you looked, your line of sight would eventually hit a star. Every single point in the sky, given enough distance, should land on a burning surface somewhere. The whole sky, by that logic, should glow, not with the gentle scatter of a few thousand visible points, but with an unbroken wall of light, as bright as the surface of the sun itself, day and night alike. This puzzle even has a name. It's called Olber's paradox, after the astronomer who wrote about it in the early 19th century, although versions of the question go back further still. For a long time, nobody could fully explain why the sky wasn't like that. Some tried to argue that dust between the stars blocked the distant light, but that explanation doesn't hold up because over enough time, dust would simply absorb the heat and begin glowing itself. The real answer turned out to be something far stranger than dust. The universe is not infinite in age. It had a beginning a finite number of years ago, and because light travels at a fixed, limited speed, there hasn't been enough time since that beginning for light from the most distant possible stars to have reached us yet. The sky is dark, not because there isn't enough universe out there, but because there hasn't been enough time for all of it to arrive. There's a second piece to the answer, layered gently on top of the first. Even the light that has reached us has been stretched and dimmed by the expansion of space itself. As the universe grows, the light traveling through it gets pulled out to longer, redder wavelengths, and loses energy along the way. Some of the earliest light in the universe has been stretched so far that it no longer even counts as visible light at all. It arrives instead as faint microwaves, spread thin across the whole sky, far too weak for our eyes to register as anything but darkness. So the black sky above you tonight isn't empty. It's simply young, in cosmic terms, and it's whispering rather than shouting, because the very fabric it traveled through has stretched its voice into something too quiet, too low, too soft for us to hear it as light. There is a wall of light surrounding all of us, and we've been looking straight through it every single night without knowing it was there. Scientists call it the cosmic microwave background, though the more poetic among them sometimes call it the afterglow of creation. Roughly 380,000 years after the beginning of the universe, something changed. Before that point, the universe was too hot and too dense for light to travel freely. Space itself was filled with a churning plasma, charged particles bouncing off each other so constantly that any beam of light would be scattered almost instantly, the way fog scatters the beam of a flashlight. There was light everywhere, but nothing could see very far through it. It was a universe made of glowing static. Then, as everything cooled and expanded, something shifted. Electrons and protons finally settled down enough to combine into neutral atoms, and space became transparent for the very first time. Light that had been trapped, bouncing endlessly, was suddenly free to travel in a straight line, uninterrupted for the rest of time. That moment left behind a kind of fossil, a faint, ancient light that fills the entire sky, coming from every direction at once, arriving from a boundary so far away that we call it the edge of the observable universe in the deepest sense. This ancient light has cooled enormously since it was released. It began as something closer to the glow inside a furnace, and after nearly 14 billion years of stretching alongside the expanding universe, it now arrives as microwaves only a few degrees above absolute zero, cold, faint, and almost perfectly uniform in every direction. If you owned an old analog television and tuned it to a channel with no signal, a small fraction of that static, a few percent, was this very light, arriving after a journey older than the Earth itself. Astronomers sometimes describe this as the true horizon of the observable universe, because it marks the earliest moment light could travel to us at all. Everything before it is hidden, not by distance exactly, but by opacity. The early universe was simply too thick with light-scattering matter for anything to be seen through it directly. In that sense, this glowing wall isn't just an edge in space. It's an edge in time, a boundary drawn not by how far we can look, but by how far back seeing is even possible. Somewhere out there, hidden just past this ancient wall of light, is a stretch of cosmic history that no telescope has ever directly photographed. Astronomers have a quiet, almost affectionate name for it: the cosmic dark ages. It refers to the period right after that ancient light was released, when the universe had cooled enough to become transparent, but before the very first stars had switched on. For a stretch of roughly 1 to 200 million years, the universe existed in near total darkness, filled with hydrogen and helium gas, slowly gathering under gravity, but without a single star yet burning to light it from within. It's a strange thing to imagine. A universe that already had space, already had matter, already had the raw architecture for everything that would follow, and yet contained no light sources of its own at all. Nothing to see by, nothing to cast a shadow, just the faint, cooling afterglow from the earlier wall of light, fading slowly into the growing dark, while gravity did its patient, invisible work pulling clumps of gas together across immense stretches of empty space. Eventually, in pockets where gas had gathered densely enough, pressure and heat crossed a threshold, and the very first stars ignited. Astronomers refer to this moment as cosmic dawn, and it's thought to mark the true end of the Dark Ages. These first stars were unlike anything that exists today, likely enormous, blazing hot, and short-lived, made purely of hydrogen and helium with none of the heavier elements that later generations of stars, including our own sun, would inherit from the stars that came before them. Their light began to reionize the surrounding gas, stripping electrons free once more, and slowly, over hundreds of millions of years, the universe transformed from a dark, cooling fog into something recognizably lit, spangled with the first galaxies, the first true structures, the first true light sources in the story of everything. We haven't seen this era directly, not the way we've mapped the ancient light or photographed distant galaxies. It remains one of the true frontiers of astronomy, a stretch of time hidden just behind the wall of the earliest light, waiting for instruments sensitive enough to catch its whisper. In some ways, it's comforting to know that even now, there are chapters of the universe's story that remain unread, not lost, just not yet found. The dark isn't empty. Sometimes it's simply a place we haven't reached with enough light of our own yet. There are galaxies out there, right now, moving away from us faster than light travels, and that's not breaking any laws of physics at all. It sounds impossible at first. Nothing can move faster than light. That's one of the most solid, well-tested rules in all of science. But there's a subtle distinction hiding inside that rule, and it changes everything once you notice it. The speed limit applies to things moving through space. It says nothing at all about the speed at which space itself can stretch. Picture a loaf of raisin bread rising in the oven. Each raisin represents a galaxy. As the dough expands, every raisin drifts farther from every other raisin, not because the raisins are crawling through the dough under their own power, but because the dough itself, the space between them, is growing. A raisin sitting close to the center might drift apart from its neighbor slowly. A raisin sitting far toward the edge of the loaf will end up drifting apart from that same center raisin much faster, purely because there's more expanding dough stacked up between them. The universe behaves in much the same way. The farther away a galaxy is from us, the more expanding space lies between it and Earth, and the faster the distance between us grows. Not because the galaxy is racing through space, but because so much space is stretching in between. Past a certain distance, that stretching adds up to a rate faster than light itself, even though nothing is technically breaking the speed limit, because nothing is actually moving through the fabric of space that quickly. The fabric itself is simply growing. This has a quiet, almost eerie consequence. There is a boundary out there, called the cosmological horizon, past which any light being emitted right now will never be able to reach us. Not in a million years, not in a trillion. The space between us and that light is growing faster than the light can close the distance. It isn't that the light is too slow. It's that the gap is widening faster than anything could ever cross it. Somewhere out past that edge, whole galaxies may exist, full of stars, full of history, that our universe has already, quietly, permanently lost the ability to ever see. Every year that passes, the portion of the universe we're able to see grows slightly larger. And yet, in the very long run, the opposite is happening. These two facts sound like they contradict each other, but they're both true, and they describe two very different kinds of edges. The first edge is the one we've been circling around already tonight, the boundary of the observable universe, the sphere defined by how far light has had time to travel since the beginning. Because the universe keeps aging, every year adds a little more travel time, which means a little more distant light finally arrives, which means our observable sphere keeps very slowly, very steadily growing. There is more universe visible to us today than there was yesterday, even if the difference is far too small to ever notice in a human lifetime. The second edge, though, tells a very different story, and it involves something called dark energy, the mysterious force behind the accelerating expansion of the universe. Unlike ordinary gravity, which pulls things together, dark energy appears to be pushing space apart, and it's doing so at an increasing rate. As the expansion accelerates, more and more distant galaxies are being pushed past that cosmological horizon we just discussed, the boundary beyond which their light can no longer ever catch up to us. Even though our observable sphere is technically still growing in radius, the number of galaxies whose light will ever be able to reach us in the future is shrinking. Some of that expansion has already carried certain galaxies permanently out of reach. Their light, emitted today, would simply never arrive, no matter how much time passed. Physicists sometimes describe this as living inside a slowly closing horizon, even while the observable sphere itself continues to widen. It's a strange, layered kind of truth, like a lantern that burns brighter even as the room around it slowly darkens. Billions of years from now, astronomers on Earth, if anyone remains to look upward, would see a night sky far emptier than ours. Most distant galaxies faded permanently beyond reach, with only our own gravitationally bound neighborhood of galaxies still visible, drifting together in an otherwise darkening universe. For now, though, none of that is close. The stars above you tonight are still arriving. The light is still traveling. And there is, at least for a very long while yet, more universe becoming visible to us with every year that passes, quietly, patiently, one photon at a time. Fact 7. A black hole doesn't have a surface in the way a planet does. What it has instead is something closer to a point where the rules of escape simply stop working. Physicists call this boundary the event horizon, and it might be the single strangest kind of edge in the entire universe, because unlike the edge of the observable universe, this one is a genuine barrier. It isn't a limit of what we happen to be able to see. It's a limit of what can ever come back out. Inside a black hole, gravity has become so overwhelming that the escape velocity, the speed something would need to break free, exceeds the speed of light itself. And since nothing can travel faster than light, nothing that crosses this boundary can ever return, not a spacecraft, not a particle, not even light. That's the origin of the name. Light goes in, light does not come back out. From outside, the region simply appears black, a silent void stitched into the fabric of space. What's strange is that the event horizon isn't a physical wall in the usual sense. There's no surface to strike, no material barrier to bump into. If you were falling toward a sufficiently large black hole, you might cross the event horizon without feeling any dramatic, singular moment. No jolt, no wall, no signal announcing you'd passed a point of no return. The danger isn't a barrier you hit. It's a threshold you cross, quietly, after which the geometry of space itself has been so warped that every possible path forward leads only inward, the way every road on a map might, past a certain point. only ever lead further into a single canyon. Outside observers, watching someone fall toward that boundary, would see something even stranger. Because gravity that intense also slows the passage of time nearby, an outside observer would never actually see the falling object cross the horizon at all. They'd see it approach more and more slowly, its light stretching and dimming, fading toward the edge, but never, from the outside observer's perspective, quite arriving, frozen, in a sense, at the very edge of visibility, forever approaching a boundary it has already, from its own perspective, silently crossed. It's one of the places in physics where two honest descriptions of the same event contradict each other completely, depending entirely on where you're standing to watch it happen. A reminder that even something as fundamental as when an event occurs isn't always a simple, shared fact in this universe. Some physicists suspect that the universe might not have an edge at all, not because it goes on forever, but because it might curve back into itself. This idea asks you to set aside a very deep, very old assumption. The assumption that space is like a room, a container with walls somewhere, even if those walls are impossibly far away. Modern cosmology offers a stranger possibility. Space itself might have an overall curvature, much like the surface of a sphere, except stretched into 3 dimensions instead of 2. Think about the surface of the Earth for a moment. It's finite. You could, in principle, measure its total area, and yet it has no edge. You could walk in a single direction for years and never once run into a wall, a fence, or a drop into nothingness. Eventually, if you kept walking, you'd simply arrive back where you started, having circled the whole surface without ever encountering a boundary. The Earth's surface is finite but unbounded, a shape with a limited size and absolutely no edge anywhere within it. Some cosmological models suggest space itself could work the same way, just with one more dimension folded into the curve. If that's the case, then someone traveling in a perfectly straight line, indefinitely, in any direction, might eventually find themselves approaching their own starting point from what appears to be the opposite direction, not because they turned around, but because space itself looped back on itself the entire time, the way a straight line on the surface of a globe eventually becomes a circle. Current measurements of the universe's large-scale geometry suggest it's very close to flat, at least within the portion we can observe, which makes this kind of curvature difficult to detect if it exists at all. The curve, if it's there, might simply be far too gentle, spread across a distance so vast that our observable universe only captures a portion too small and too flat-looking to reveal it. It's a bit like standing in a single field and trying to determine, just from that field alone, whether the ground beneath you belongs to a flat plane or the surface of an enormous, gently curving planet. From where you're standing, both would look exactly the same. There may be far more universe out there than we will ever be able to prove exists, and the honest, careful answer to how much more is simply that nobody knows. This is one of the places where science becomes remarkably humble. The observable universe, the region whose light has had time to reach us, is enormous by any human measure, tens of billions of light years across in every direction. But nearly every model of cosmic inflation, the theory describing an extremely rapid expansion in the universe's earliest fraction of a second, suggests that the full universe, the one that exists beyond what light has had time to show us, is very likely far larger still. Some versions of these models suggest it could be many times larger than what we can observe. Others suggest it could be effectively infinite. The unsettling part, for anyone who likes clean, testable answers, is that this may be a question science can never fully resolve, not because we haven't built strong enough telescopes yet, but because of a limit built into the very structure of the observable universe itself. No matter how advanced our instruments become, we will never be able to see past the point where light simply hasn't had time to arrive. That limit isn't a matter of technology. It's a matter of the universe's age and the fixed speed of light, both of which set a hard boundary on how far our looking can ever reach, regardless of how good our eyes get. So astronomers are left in a strange and honest position, working with excellent evidence about the portion of the universe within reach, while acknowledging that the true size of everything that exists might remain permanently, structurally unknowable. It isn't a failure of science. It's simply an honest edge to what observation, by its very nature, can ever offer. There is a difference between something being false and something being simply out of reach, and much of the universe beyond our horizon likely falls into the second category, real, presumably, but permanently unconfirmed. If you could travel to the very edge of what any telescope has ever detected, you would find something that looks less like a boundary and more like a smudge of red light, barely holding together. Astronomers have identified galaxies whose light has been traveling toward us for more than 13 billion years, meaning we're seeing them as they existed when the universe itself was only a few hundred million years old. Infants, cosmically speaking, caught in their earliest stages of formation. These are some of the most distant objects ever confirmed, and finding them takes extraordinary patience, because their light has been stretched so dramatically by the universe's expansion that it arrives not as visible light at all, but shifted deep into the infrared, requiring space telescopes built specifically to detect wavelengths our eyes were never designed to see. This stretching effect is called redshift, and it works a bit like the changing pitch of a passing ambulance siren, except with light instead of sound. As a light source moves away from an observer, or as the space between the source and the observer expands, the light waves get stretched out, shifting toward longer, redder wavelengths. The more extreme the redshift, the more extreme the distance, and the further back in time astronomers are actually looking. What's remarkable is how faint and fragile these earliest galaxies appear compared to galaxies today. They're often smaller, more chaotic in shape, still in the process of assembling themselves from clumps of gas and young stars. Nothing like the vast, elegantly spiraled or elliptical galaxies that fill the more nearby, more mature universe. Looking at one of these distant, early galaxies is a little like finding a photograph of a place you know well, but taken so long before you knew it that almost nothing about it looks the way you'd expect. The location is the same. The moment in its history is almost unrecognizably different. Every time astronomers manage to detect a galaxy slightly more distant than the last record holder, they aren't just adding a new entry to a list of impressive numbers. They're pushing the edge of human sight a little closer to the very beginning of everything, one faint red smudge of ancient light at a time. There's a theoretical structure in physics that would let you travel between two distant points in the universe without crossing the space in between at all. Though as far as anyone can tell, nature has never actually built one. It's called a wormhole, and it emerges as a mathematically valid solution to the equations of general relativity, the same theory that describes gravity, black holes, and the curvature of space itself. The idea, in its simplest form, imagines two distant regions of space connected by a kind of tunnel or bridge, folding the fabric of space-time so that 2 points, ordinarily separated by an unimaginable distance, become neighbors through this connecting passage. A useful way to picture it is to imagine a flat sheet of paper representing the universe, with 2 dots drawn far apart to represent 2 distant locations. To travel between them the ordinary way, you trace a long line across the paper's surface. But if you folded that paper in half instead, bringing the two dots close together, and then pushed a pencil straight through both layers, you'd create a shortcut, a tunnel connecting 2 points that remain just as far apart along the paper's surface as they always were. The trouble is that everything we understand about wormholes remains purely theoretical and quite possibly impossible in practice. The equations allow for their existence, but maintaining one, keeping the passage open long enough and stable enough for anything to travel through, appears to require a form of matter with genuinely bizarre properties, something scientists call negative energy or exotic matter, which has never been confirmed to exist in any meaningful quantity, if it exists at all. Even in the most optimistic theoretical models, a wormhole left unsupported would likely collapse in on itself far too quickly for anything to pass through, snapping shut in a fraction of a second. Still, the fact that these structures emerge naturally from trusted, well-tested equations, whether or not the universe has ever bothered to build one, tells us something curious about the edges of physical possibility. Sometimes the mathematics allows for a door that nature, for reasons we don't yet understand, may have simply chosen never to open. Our entire universe, everything we have ever measured, ever seen, ever touched, might be nothing more than a single bubble floating among an uncountable number of others. This idea goes by the name the multiverse, and it isn't one single theory so much as a family of related ideas that different branches of physics arrive at independently, almost as if several separate roads all happen to lead toward the same strange destination. One version comes from inflation theory, the same framework describing the universe's earliest, explosive expansion. Some models of inflation suggest that this rapid expansion wasn't a single, one-time event. Instead, it may have continued eternally in most places, with our own universe forming as one local region where inflation happened to stop, like a single bubble forming and settling within a vast, still boiling pot, surrounded by countless other bubbles doing the very same thing, each one becoming its own separate, self-contained universe, permanently disconnected from all the rest. Another version arrives from an entirely different direction, through the mathematics of quantum mechanics, the physics governing the smallest scales of reality. Some interpretations suggest that every quantum event with multiple possible outcomes doesn't simply resolve into one outcome while the others vanish. Instead, every possible outcome occurs, each one branching off into its own separate, equally real timeline, endlessly splitting the universe into new versions of itself with every quantum decision made anywhere by anything. None of these ideas currently have direct observational proof, and it's worth being honest about that, because it's part of what makes them fascinating rather than settled fact. They emerge from equations that have proven remarkably accurate in every other context we've tested them in, which is exactly why physicists take the possibility seriously rather than dismissing it outright, even while acknowledging that a genuinely separate universe, by most definitions, could never send us a signal, a particle, or a single photon of proof. If other universes exist, they may be the one kind of edge that isn't just difficult to see past. It may be a kind of edge that, by its very definition, nothing could ever cross to confirm from either side. Long before anyone had telescopes powerful enough to test it, some of the very earliest philosophers already suspected that the universe might have no true edge at all, and they were arguing about it for reasons that had nothing to do with astronomy. Around the 5th century BCE, a philosopher named Archytas posed a simple but stubborn question. If you traveled to the very edge of the universe and reached out your hand, what would happen? Either your hand would extend past the boundary, proving the edge wasn't really the edge after all, or it would somehow be stopped by something. And if something stopped it, that something must itself exist, occupying space, meaning the edge wasn't truly an edge either. Either way, he argued, you'd be forced to conclude that space simply continues, that a genuine boundary to the universe was almost logically impossible to construct without contradiction. It's a strikingly clever thought experiment for its time, built entirely from reasoning rather than observation, and it echoes forward across more than 2,000 years into modern physics in a surprising way. Today, cosmologists no longer frame the question in quite those terms, since our understanding of space, curvature, and expansion is far more sophisticated than anything available to ancient philosophy. But the underlying intuition that a hard, final edge to everything is peculiarly difficult to make logical sense of still echoes through modern thinking about a universe that may be infinite, or curved back on itself, or simply larger than anything we could ever measure. There's something quietly moving about that continuity, the idea that a person sitting outdoors more than 2,000 years ago, with no telescope, no satellite, nothing but careful thought and the night sky above them, was already circling the same edge we're circling tonight. The instruments have changed enormously. The wonder, apparently, has not changed at all. The universe isn't scattered randomly, like sand thrown across a floor. On the largest scales, it forms something closer to a vast, glowing web, with galaxies strung along threads and clustered at knots, surrounded by enormous stretches of near-total emptiness. Astronomers call this arrangement the cosmic web, and mapping it required decades of patient, painstaking work, measuring the position and distance of galaxy after galaxy until a pattern began to emerge from what had once looked like scattered points. What they found was structure at almost every scale. Galaxies cluster into groups. Groups gather into larger clusters. Clusters connect to one another through long, thin filaments of galaxies and gas, stretching across hundreds of millions of light years, like threads of a spiderweb cast across unimaginable distances. And nestled between these filaments are voids, enormous regions of space containing only a small fraction of the galaxies found elsewhere, some of them so empty and so vast that light takes hundreds of millions of years just to cross from one side to the other. One of the more striking things about this structure is how it came to exist at all. It traces its origins back to incredibly tiny fluctuations in the density of the very early universe. Differences so small they're measured in fractions of a percent, imprinted into the fabric of everything within the first fraction of a second after the beginning. Regions that started out just barely denser than average slowly attracted more matter through gravity, growing denser still over billions of years, while the already sparser regions grew emptier by comparison as their matter drifted away, pulled toward the growing structures nearby. Tiny differences, almost too small to measure, patiently amplified over billions of years into the largest structures ever observed. Some of the individual features within this web carry genuinely staggering measurements. Certain filaments and superclusters stretch across distances so large that light, moving at its full, uninterrupted speed, would need well over 1 billion years just to travel from one end to the other. It's difficult to hold a number like that in your mind for very long. Perhaps it's easier simply to imagine it as a single, enormous piece of lace stretched across the dark, with galaxies caught glittering along every thread. There are ripples moving through the fabric of space right now, passing straight through you, your bed, and everything in this room, and you will never feel a single one of them. These are called gravitational waves, and they're created whenever extremely massive objects accelerate violently through space. Most dramatically, when two black holes or two neutron stars spiral into one another and collide. The collision itself doesn't just release energy as light or heat. It sends ripples directly through the structure of space-time, stretching and compressing space itself as the wave passes, ever so slightly, in every direction it travels. For 100 years after Einstein's equations first predicted their existence, gravitational waves remained purely theoretical, far too faint by the time they reached Earth for any instrument to detect. The distortion they cause, even from a catastrophic collision happening a billion light years away, is almost impossibly small by the time it arrives here, changing the distance between 2 points on Earth by a fraction smaller than the width of a proton. It wasn't until highly sensitive detectors, built specifically to measure distortions that minuscule, finally succeeded in catching one, a discovery that opened an entirely new way of observing the universe, one that doesn't rely on light at all. What makes this especially interesting in the context of edges and boundaries is that gravitational waves can reach us from places light never could. A pair of black holes merging produces no light whatsoever, since black holes, by definition, emit none. An event like that would be completely invisible to every telescope ever built, a silent, dark collision lost entirely to conventional astronomy. But gravitational waves carry the signature of that event outward regardless, rippling through space and eventually washing over Earth, detectable by instruments built to listen rather than to look. In a very real sense, this gives us access to an entirely separate category of edge, events and objects that sit permanently beyond the reach of light-based observation, yet remain within reach of a completely different sense, one humanity only learned to use within the last several years. It's a reminder that the boundary of what we can know isn't fixed. Sometimes it simply waits for us to develop a new way of listening. In the almost unimaginably distant future, long after everything familiar about the night sky has changed beyond recognition, the universe is expected to settle into something physicists sometimes call, quite simply, the dark era. This isn't a prediction about tomorrow, or even about anything within a timescale a person could meaningfully picture. It concerns trillions upon trillions of years from now, long after every star currently burning has exhausted its fuel, long after new stars have stopped forming altogether because the raw material needed to build them has finally run out. Even the smallest, most miserly stars, the ones expected to burn dimly for the longest stretches of time, are thought to eventually fade, leaving behind cooling remnants scattered through an increasingly empty universe. Layered on top of this slow fading is the ongoing expansion we discussed earlier tonight, the one being accelerated by dark energy. Over spans of time this vast, that expansion is expected to carry nearly every other galaxy so far beyond our own that they'll drift permanently past the cosmological horizon, disappearing not because they've been destroyed, but simply because the space between us and them will have stretched too far, too fast, for any of their light to ever reach us again. A future observer, however far off, might look upward into a sky containing only the faded, merged remnants of galaxies gravitationally bound to our own, an island, drifting alone, in an otherwise blank and silent dark. It's a strange kind of ending to imagine, not with a single dramatic event, but with a slow, patient fade stretched across a timescale so long that someday barely captures it. And yet, oddly, many physicists don't describe this future as bleak so much as simply vast, a natural continuation of the same processes already unfolding tonight, above you, at a pace too slow for any human lifetime to notice. It's worth remembering, sitting here tonight, that none of this touches us. Not this year, not this millennium, not for a length of time that dwarfs every recorded moment of human history laid end to end. The stars above you now will still be there tomorrow night, and the night after that, keeping their slow, unhurried pace toward an ending so distant it barely qualifies as the future at all. There's a number tucked inside cosmology that quietly resolves one of our 3 questions from earlier tonight. The one about what the universe could possibly be expanding into. The honest answer, as strange as it sounds, is probably nothing. Not nothing in the sense of empty space waiting outside. Nothing in the sense that the question itself may be built on a small, understandable mistake. When people imagine the universe expanding, it's natural to picture something like a balloon inflating into a room, growing to fill space that was already there, empty and waiting beyond its surface. But that image accidentally imagines something existing outside the universe for it to expand into, and cosmologists generally don't think that's how it works at all. Space, in this framework, isn't a thing sitting inside some larger container. Space is everything. It doesn't need an outside to expand into any more than a number needs a place to exist in order to get larger. When cosmologists say the universe is expanding, they mean the distances between points within space are increasing, not that space is spreading into some pre-existing external void. If you imagine the surface of that same balloon we mentioned earlier, but strip away the idea of the balloon's interior and exterior entirely, focusing only on the 2-dimensional surface itself, you get a slightly better picture. Dots drawn on that surface move apart from each other as the surface stretches, without ever needing anything outside the surface to expand into. The surface simply is the whole of what exists in that simplified picture, and it grows because the space that makes it up is growing. It's a genuinely difficult idea to hold in the mind, because human intuition is built entirely around objects existing inside other, larger spaces. We rarely, if ever, encounter something that has no outside at all. But that may be exactly what the universe is, not a thing sitting in some larger emptiness, expanding to fill it, but the entire fabric of existence itself, quietly becoming more spread out, with nothing beyond it required, or perhaps even meaningful, to ask about. After everything we've covered tonight, distances beyond counting, light older than any world, boundaries that might not even be boundaries at all, there's a small, almost funny fact worth ending on. Nobody, anywhere, actually knows if the universe is finite or infinite. It's one of the biggest open questions in all of cosmology, and it remains genuinely, honestly unresolved. Every measurement taken so far suggests the observable portion of the universe is very close to geometrically flat, which is consistent with an infinite universe, but it's equally consistent with an extremely large, gently curved, finite one, simply too enormous for our instruments to detect the curve within the small patch we're able to observe. The data doesn't currently rule either possibility out, and it's entirely possible it never will, given the fundamental limit on how far light has had time to travel toward us since the beginning. This is, in its own way, a fitting place to end, because it captures something true about the whole subject of tonight's journey. We've spent hours circling something we can measure with extraordinary precision in some places, and something that remains fundamentally, structurally unknowable in others. Both of those things are true about the universe at the very same time. It is one of the most thoroughly measured subjects human beings have ever studied, and it is also, at its outermost edges, one of the last true mysteries left completely open, waiting patiently for a future far ahead of us, or perhaps waiting forever. Maybe that's the shape the edge of space was always going to take, not a wall, not a line, not a place any spacecraft could ever land on, but a soft, honest boundary between what we've managed to learn and what remains, for now, gently and permanently out of reach. There's a spacecraft, launched in 1977, that has already crossed one very real, very physical edge of space, and it's still sending back a faint signal, more than 20 billion kilometers from home. Its name is Voyager 1, and for decades it traveled outward through our solar system, past Jupiter, past Saturn, capturing some of the most striking images of the outer planets ever taken. But its most quietly remarkable achievement came later, long after the planetary flybys were finished, when it kept going patiently into the space beyond. Our sun doesn't simply stop influencing its surroundings at some fixed line. It constantly releases a stream of charged particles called the solar wind, which pushes outward in every direction, carving out a vast, bubble-shaped region of space known as the heliosphere. Inside that bubble, the sun's influence dominates. Outside it lies interstellar space, filled instead with material and radiation from the wider galaxy. The boundary between the two, where the pressure of the solar wind finally gives way to the pressure of interstellar space, is called the heliopause, and it's about as close as human engineering has ever come to touching a genuine, physical edge of our solar system. In August of 2012, after 35 years of travel, Voyager 1 crossed that boundary, and its instruments recorded a sudden, measurable shift, a drop in particles associated with the sun, a rise in particles arriving from elsewhere in the galaxy. For the first time, a human-built object had left the space governed by our star and entered the space between stars, a region scientists refer to simply, and rather beautifully, as interstellar space. It's worth sitting with how far that actually is, and how long it actually took. Light from the sun, moving at its full, uninterrupted speed, takes over 20 hours to reach Voyager 1's current position. A signal sent from the spacecraft today, traveling at the speed of light, takes roughly that same stretch of time just to reach the antennas listening for it back on Earth. And yet, even at that unimaginable distance, Voyager 1 still hasn't reached anything resembling the edge of the universe, or even the edge of our galaxy. It has only left the small, local bubble carved out by a single, ordinary star. The true edges of space, the ones we've spent tonight exploring, remain farther away than any spacecraft could reach in 1,000 human lifetimes, let alone one. Still, there's something moving about a small, aging machine, built decades ago with less computing power than the device most people fall asleep next to each night, quietly continuing outward long after everyone who built it imagined it would still be listening, still speaking, still crossing edges, one patient kilometer at a time. If you could average together the light from every star, every galaxy, every glowing thing in the observable universe, the result wouldn't be white, or gold, or a deep cosmic black. It would be a soft, pale beige, closer to the color of a lightly milked coffee than anything most people would associate with the vastness of space. Astronomers actually gave this color a name, half jokingly, half affectionately: cosmic latte. It emerged from a study that gathered light from over 200,000 galaxies, blending their combined color together the way you might mix a huge palette of paints into a single average shade. The result surprised almost everyone involved, because it broke so completely from the popular image of space as a place defined by inky blackness dotted with sharp, cold points of light. The reason for that soft, warm tone comes down to the kinds of stars that dominate the universe's light output. Younger stars tend to burn with a bluer light, while older, cooler stars glow more toward the red end of the spectrum. When you average the combined light of billions of galaxies, filled with stars across every stage of life, the blues and the reds and the yellows blend together into something gentle and neutral, a shade that, if you held a paint swatch up to it, would look entirely at home on the wall of a quiet, softly lit room. There's something almost tender about that discovery. For all its scale, for all its ancient light and unreachable distances, the universe's overall color, averaged across everything we can observe, turns out to be something warm, something soft, something closer to candlelight than to cold, distant space. It's not the color most people picture when they imagine looking outward into everything that exists. But perhaps it should be. Every direction you could possibly look, across the entire sky, shows a universe that looks remarkably, almost suspiciously similar, and explaining why turned out to require rewriting our understanding of the universe's very first moments. This is known among physicists as the horizon problem, and it's one of the more elegant puzzles in cosmology. The ancient light we discussed earlier tonight, the cosmic microwave background, arrives from every direction in the sky at nearly the same temperature, varying by only the tiniest fractions of a degree no matter which direction you measure it from. On the surface, that might not sound strange, but consider what it implies. Two patches of that ancient light, arriving from opposite sides of the sky, come from regions of the early universe that, by any conventional calculation, would never have had enough time to interact with each other, to exchange heat, to reach the same temperature the way two objects placed side by side naturally would. They were, according to the standard expansion rate, simply too far apart, too early in cosmic history, for any signal, even one traveling at the speed of light, to have passed between them. And yet, somehow, they match almost perfectly. It's a little like discovering that two strangers on opposite sides of the world, who have never met, never communicated, and never shared any information, happen to arrive at the exact same answer to a complicated question, independently, purely by coincidence. It doesn't sit comfortably with how cause and effect are supposed to work. The leading explanation involves a theory called cosmic inflation, the idea that in an unimaginably brief fraction of a second after the very beginning, the universe underwent an extraordinarily rapid burst of expansion, stretching space far faster than light itself, though again, without breaking the actual speed limit, since it was space doing the stretching, not anything moving through it. Before that inflationary moment, the theory suggests the entire visible universe was compressed into a region small enough that everything within it could, in fact, interact and reach the same temperature quite easily. Then, in an instant, that tiny, evenly warmed patch was stretched out to become the enormous universe we observe today, carrying its earlier uniformity along with it, stretched but preserved, like a single evenly mixed drop of dye pulled out into a vast, gently varied wash of color. It's a theory that neatly explains a puzzle that otherwise has no easy answer, though like several ideas tonight, it remains an area of active research rather than a settled, closed case. Sometimes the most convincing answer in physics isn't the one that's fully proven. It's simply the one that quietly explains everything else we can already measure better than any of the alternatives. There's a kind of star out there so dense that a single teaspoon of its material would weigh roughly as much as a mountain. And it sits right at the edge of how much matter can be compressed before it collapses into something even stranger. These are neutron stars, and they form from the collapsed cores of massive stars that have run out of fuel and exploded as supernovae. What remains afterward isn't a normal collection of atoms anymore. The collapse is so violent, the gravity so overwhelming, that electrons and protons are crushed together into neutrons, packing the leftover material into a sphere often no larger than a city, while still containing more mass than our entire sun. The physics that keeps a neutron star from collapsing any further is itself a kind of edge, a boundary between one stable state of matter and a far stranger one. A principle from quantum mechanics, which prevents certain particles from occupying the exact same state as one another, creates an outward pressure strong enough, in most cases, to balance against the star's own crushing gravity. This delicate standoff holds the star together in its current form. But that balance only works up to a certain mass. Beyond a specific threshold, calculated by physicists as a rough dividing line, even that pressure isn't enough. Gravity wins entirely, and the collapse continues without any known force able to stop it, forming a black hole instead. In this sense, a neutron star represents matter existing right at the very outer limit of what can remain stable before physics runs out of ways to hold it together. It's one of the densest, most extreme forms of matter known to exist anywhere in the universe, spinning in some cases hundreds of times per second, sweeping beams of radiation across space with the mechanical precision of a lighthouse built from the collapsed heart of a dead star. Astronomers have even detected some spinning fast enough that their surface, at the equator, moves at a meaningful fraction of the speed of light itself. A genuinely strange thought to hold, tucked quietly among the calmer, gentler facts of tonight. If a small handful of numbers in physics were even slightly different from what they are, nothing in this room, nothing in this galaxy, nothing capable of asking questions about the universe at all, would likely exist. Physicists refer to this observation as fine-tuning, and it centers on the strange precision of the fundamental constants that govern our universe. Numbers like the strength of gravity, the strength of the force holding atomic nuclei together, and the particular masses of basic particles. These values aren't derived from some deeper, more fundamental principle that forces them to be what they are. As far as anyone currently understands, they simply are what they are, measured rather than explained, and many of them appear to sit within a remarkably narrow range that allows for a universe complex enough to form stars, planets, chemistry, and eventually life. Consider gravity. If it were even slightly stronger, relative to the other forces, stars would burn through their fuel far too quickly, collapsing long before life of any complexity could have time to develop nearby. Slightly weaker, and matter might never have gathered densely enough to ignite stars at all, leaving the universe filled only with cold, diffuse clouds of gas, drifting forever without a single point of light. Similar sensitivities appear in the force binding atomic nuclei together, adjusted only slightly in either direction, and the specific nuclear reactions responsible for building the heavier elements found throughout the universe, including the elements making up this room, this bed, and you, simply wouldn't occur the way they do. There are several ways physicists have approached this puzzle, and none of them are fully settled. Some suggest it's simply the way things happen to be, without any deeper explanation required. In the same way you don't need an explanation for why a coin landed on a particular side after being flipped exactly once. Others point back toward the multiverse ideas we touched on earlier tonight, suggesting that if countless separate universes exist, each with its own randomly determined constants, it would be entirely unremarkable that we happen to find ourselves in one of the rare universes where the numbers worked out well enough for observers to exist in the first place, simply because we couldn't possibly be asking the question from inside any of the universes where they didn't. It's an edge of a very different kind than the ones we've discussed so far tonight, not a boundary in space, but a boundary in possibility itself. The narrow range of values separating a universe capable of producing something as improbable as a mind, resting quietly in a bed, wondering about all of this, from the vastly larger range of universes that, as far as we can tell, would have produced nothing capable of wondering about anything at all. The very first edge the universe ever had wasn't a place. It was a moment. Most of tonight, we've been talking about edges scattered through space, boundaries of light, boundaries of observation, boundaries of physical law. But cosmologists increasingly describe the true starting point of everything, the event sometimes called the Big Bang, not as a location you could point to somewhere in the sky, but as an edge in time itself, a beginning past which the very concept of before appears to stop making sense. This is a genuinely strange idea to sit with, because human beings are used to time working in only one direction, endlessly, with every moment having some earlier moment behind it. But general relativity, the same framework that describes gravity, black holes, and the curvature of space, suggests that time itself is woven together with space into a single combined fabric, one that appears to have had a beginning, roughly 13.8 billion years ago, at which the usual rules describing how time flows may simply break down entirely. Asking what happened before the Big Bang, under this framework, may be a bit like asking what lies north of the North Pole. It isn't that the answer is difficult to find, or hidden somewhere we haven't looked yet. The question itself may not point toward anything meaningful, because before is a concept built entirely around the existence of time passing, and time, in the most widely supported models, appears to have begun at that very moment, rather than having stretched backward endlessly beforehand. Some newer theoretical models do attempt to describe a before, involving ideas like a prior contracting universe, or an endless cycle of expansions and collapses, but none of these have found solid observational support yet, and they remain firmly in the territory of speculation rather than confirmed science. So perhaps this is the deepest, quietest edge of the whole subject. Not a wall in space, not a horizon of unreachable light, but the very edge of time itself, standing at the beginning of everything, patient and unmoving, marking the one boundary that doesn't recede no matter how far our instruments someday reach. Our entire galaxy, along with thousands of others nearby, is being pulled steadily towards something enormous, hidden almost directly behind the plane of our own Milky Way. And for a long time, nobody could even see what it was. Astronomers first noticed the pull in the 1970s, while mapping how galaxies in our cosmic neighborhood were moving. Instead of drifting apart evenly with the general expansion of the universe, a huge number of galaxies, spread across an enormous region of space, all appeared to be accelerating gently toward one particular direction, as though something massive were quietly tugging at the fabric of space around it. They gave this mysterious pull a fittingly dramatic name, the Great Attractor. Locating it directly turned out to be unusually difficult, not because it was too faint or too far, but because of where it happened to sit in the sky. From our vantage point, the Great Attractor lies almost directly behind the dense, dusty plain of our own galaxy, a region astronomers sometimes call the zone of avoidance, where thick clouds of gas and dust block most visible light from anything behind them. It was a bit like trying to identify a mountain range hidden behind a curtain, using only the way the curtain occasionally rippled from something pressing against it from the other side. Eventually, using telescopes sensitive to X-rays and radio waves, wavelengths capable of passing through that obscuring dust more easily than visible light, astronomers confirmed the source. The Great Attractor turned out to be an enormous concentration of galaxy clusters, an immense structure containing the mass of many thousands of galaxies combined, sitting roughly 200 million light-years away. And in an even stranger twist, later observations revealed that the Great Attractor itself appears to be moving too, drawn onward by something even larger and more distant still, an enormous collection of galaxy clusters sometimes called the Shapley supercluster, one of the most massive structures known anywhere in the observable universe. It's a strange thing to consider, lying still in a quiet room tonight, that the galaxy holding your solar system, your planet, and this very moment, is itself drifting, slowly and imperceptibly, pulled by the gravity of something so large it took decades just to locate it, hidden the entire time in plain sight, tucked just behind the dust of our own galactic home. Somewhere in the night sky, currently, is a galaxy on a slow, patient collision course with our own, and the timeline for that meeting is so long that it poses absolutely no reason for concern tonight, or for a very, very long stretch of nights after this one. That galaxy is Andromeda, our nearest large galactic neighbor, sitting a little over 2 million light-years away. Even at that staggering distance, precise measurements of its motion show it moving steadily closer to the Milky Way, drawn in by the mutual gravity between our two galaxies. Current estimates suggest the two will begin to merge in roughly 4 to 4.5 billion years, a stretch of time so long that our Sun itself is expected to have changed dramatically by the time it arrives, swelling into a much larger star as it nears the end of its own life cycle. Despite the dramatic word collision, the actual event is expected to unfold gently, at least on the scale of individual stars. Galaxies are mostly empty space, with enormous distances separating one star from the next. When two galaxies merge, the overwhelming majority of their individual stars simply pass by one another without ever making direct contact, their vast separations acting like widely scattered sand rather than tightly packed objects likely to collide. What changes dramatically instead is the overall shape and structure, as gravity gradually reshapes both galaxies' spiral arms, pulls streams of stars into long tidal tails, and eventually settles the combined mass into a single, larger galaxy, likely elliptical in shape, that astronomers have already given a placeholder name, Milkomeda. There's something quietly reassuring buried inside this fact, if you sit with it the right way. An event this vast, this genuinely cosmic in scale, is already written into the future with remarkable confidence, computed and modeled and understood in detail by scientists working right now. And yet it changes nothing about tonight. It changes nothing about tomorrow or next year, or the next 100,000 years stacked end to end. The universe holds enormous, slow-moving events in its future the way a held breath holds air, patiently, without urgency, giving you every single night between now and then simply to rest. There's a region of space so empty, so strikingly devoid of galaxies, that astronomers gave it a nickname suited for something out of a folk tale, the Great Nothing. Its formal name is the Boötes Void, named for the constellation in whose direction it happens to lie, and it's one of the largest known voids in the observable universe, a roughly spherical region stretching across an estimated 330 million light-years, containing dramatically fewer galaxies than the space surrounding it. For comparison, our own cosmic neighborhood, a region of similar size, might contain many thousands of galaxies. The Boötes Void, by contrast, contains only a small handful, a few dozen at most, scattered thinly across a volume of space large enough to swallow entire clusters elsewhere without noticing the difference. When it was first discovered in the early 1980s, astronomers were genuinely startled by how empty it appeared. There's a well-known, half-joking calculation from around that time suggesting that if the Milky Way had happened to form somewhere near the center of the Boötes Void instead of where it actually sits, humanity might not have discovered the existence of other galaxies until sometime in the 1960s, simply because there would have been so little nearby to detect with the telescopes available before then. A strange thought considering how central the study of other galaxies has become to modern astronomy. The void isn't perfectly empty, and modern surveys, with far more sensitive instruments than those available decades ago, have found a modest scattering of galaxies within it that earlier searches missed, threading faintly through what once looked like complete emptiness. But it remains dramatically underdense compared to the cosmic web structure we discussed earlier tonight, a genuine, vast pocket of near-nothing tucked among the great filaments and clusters that fill most of the rest of the universe. It's a humbling reminder that scale, out here, doesn't always mean abundance. Sometimes the largest structures in the universe are defined not by what fills them, but by how much they simply, quietly, leave empty. Some of the most distant objects ever photographed weren't found because they were bright enough to see directly. They were found because something else, something massive and completely invisible, happened to bend space itself into a natural, cosmic magnifying glass. The effect is called gravitational lensing, and it comes directly from Einstein's description of gravity as a curvature in the fabric of space itself, rather than a simple pulling force. Massive objects, like galaxy clusters, don't just attract nearby matter. They actually warp the space around them. And since light travels through space, that warping bends the path of light passing nearby, the way a lens made of glass bends light passing through it, just on a far larger, more elegant scale. When a massive galaxy cluster happens to sit directly between Earth and a much more distant object, its gravity can bend and focus the light from that background object, magnifying it, sometimes dramatically, occasionally even splitting a single source into multiple visible images arranged around the lensing cluster, or stretching it into long, curved arcs of light. Astronomers have used this effect deliberately, treating certain massive galaxy clusters as natural telescopes far more powerful than anything humanity could build directly, allowing them to observe galaxies so distant and so faint that they would otherwise be completely undetectable, hidden below the sensitivity of even our most advanced instruments. There's something quietly poetic about that. Some of our clearest views of the earliest, most distant edges of the observable universe haven't come from staring harder or building bigger mirrors alone. They've come from happening to look through exactly the right stretch of warped, borrowed space, using the universe's own gravity as a lens we didn't build and didn't design, simply positioned, by chance, exactly where we needed it to be. Most of the matter in the universe isn't the kind you can see, touch, or detect with light of any kind, at any wavelength. And after decades of searching, nobody has yet identified exactly what it actually is. This invisible material is called dark matter, and the name is really more of an honest admission than a real description. It doesn't refer to matter that's simply dark in color, the way a shadow might be. It refers to matter that doesn't interact with light at all, neither emitting it, absorbing it, nor reflecting it, making it fundamentally invisible to every kind of telescope built to observe electromagnetic radiation, regardless of how sensitive that telescope becomes. Astronomers first suspected something was missing while studying the way galaxies rotate. Based purely on the visible matter within a galaxy, stars near the outer edges should orbit the galactic center more slowly than stars closer in, the same way planets farther from the sun orbit more slowly than planets closer to it. But when astronomers actually measured galactic rotation, the outer stars were moving far too quickly for the visible matter alone to hold them in orbit through gravity. Something else had to be present, contributing significant mass without contributing any detectable light, essentially an invisible scaffold holding galaxies together more tightly than their visible contents alone could explain. Since then, evidence for dark matter has accumulated from several completely independent directions, from the way galaxy clusters bend light through gravitational lensing, to the detailed patterns found within the ancient light of the cosmic microwave background. All of this evidence points toward the same striking conclusion. The ordinary matter that makes up stars, planets, and everything we can directly observe accounts for only a small fraction of the universe's total mass. The rest, by current estimates, is dark matter, quietly outweighing everything visible by a wide margin, present in every galaxy, shaping the large-scale structure of the cosmic web we discussed earlier tonight, and yet remaining, after decades of dedicated searching with some of the most sensitive detectors ever built, essentially undetected in any direct, hands-on way. In its own strange fashion, this might be the truest edge of tonight's entire journey, not a boundary in space or in time, but a boundary in understanding itself. We can measure dark matter's effects with remarkable precision. We simply cannot yet say, with any real confidence, what it actually is. It surrounds us, holds our galaxy together, and remains, for now, one of the largest and most patient mysteries left completely open in modern physics. Most galaxies keep company. They cluster, gather, orbit one another, caught in the gravity of countless neighbors scattered nearby. But scattered here and there throughout the universe are a small number of galaxies that live an entirely different kind of existence, drifting through vast stretches of space with no other galaxy anywhere near them. Astronomers call these void galaxies, or sometimes field galaxies, and the most famous example, a galaxy called MCG plus 01, 02-015, sits at the center of a region so sparse that its nearest galactic neighbor lies roughly 100 million light-years away, a distance far greater than the separation typically found between galaxies almost anywhere else in the observable universe. To put that in perspective, our own Milky Way has dozens of neighboring galaxies within a tenth of that distance, including our eventual companion Andromeda from earlier tonight, along with countless smaller dwarf galaxies caught in our gravitational orbit. This kind of isolation has real, measurable consequences for how a galaxy evolves. Most galaxies grow and change partly through interaction, merging occasionally with smaller neighbors, having their spiral arms tugged and reshaped by passing gravitational encounters, sometimes even triggering fresh bursts of star formation when two galaxies pass close enough to disturb each other's gas clouds. An isolated galaxy, with nothing nearby to interact with, ages quite differently, developing and changing almost entirely on its own terms, undisturbed by outside gravity for what may be billions of years at a stretch. There's a particular kind of stillness in imagining a galaxy like that. 100 billion stars, countless solar systems, entire potential histories playing out across its structure, and not one single neighboring galaxy close enough to influence, disturb, or even meaningfully illuminate the sky as seen from within it. If there happened to be a planet inside that galaxy, with someone lying quietly on their back looking upward at night, its own galaxy's stars would fill the sky in every direction, and beyond that, for an almost unfathomable stretch of empty space, there would be nothing else at all. Just their own galaxy, softly glowing, alone in the deep, unbroken dark. If you wanted a single number to describe how wide the observable universe actually is, the honest number is far larger than most people expect, and understanding why requires holding two separate ideas gently, together, at the very same time. The universe is roughly 13.8 billion years old, so it might seem like the most distant light reaching us should have traveled for exactly that long, meaning the observable universe should measure about 13.8 billion light-years in radius. But the actual figure astronomers use is dramatically larger, closer to 46.5 billion light-years in every direction, making the full diameter of the observable universe roughly 93 billion light-years across. The gap between those two numbers, 13.8 billion years of travel time compared to 46.5 billion light-years of actual distance, comes entirely from something we've touched on more than once tonight: the ongoing expansion of space itself. Here's the gentle way to hold it in mind. When a beam of ancient light first left its source, billions of years ago, that source was much closer to what would eventually become Earth's location than it is today. But during the entire time that light has been traveling toward us, the space between its starting point and its destination has continued expanding, stretching the distance out further and further, even as the light itself continued moving through it. By the time that ancient light finally reaches us, the object that originally sent it has since drifted much farther away, carried outward by the universe's ongoing expansion, even though the light took a much shorter, more direct path measured purely by travel time. So the distance we measure today, describing where that light source currently sits, is considerably larger than the distance the light itself appears to have traveled, based simply on multiplying its age by the speed it moves. Both numbers are true. They're just answering slightly different questions, one about how long a journey took, and one about how far apart the two ends of that journey actually are, right now, after everything that expanded quietly in between. It's a strange, layered kind of arithmetic, but it captures something true about nearly everything we've discussed tonight. So much of cosmology isn't really about finding a single correct number. It's about learning to ask the question carefully enough that the number you get actually means what you think it means. There's a second ancient signal, even older than the wall of light we discussed earlier tonight, drifting through the universe right now. And unlike that first signal, nobody has ever managed to detect it directly. We spent time earlier discussing the cosmic microwave background, the ancient light released roughly 380,000 years after the beginning, once the universe cooled enough to become transparent. But there's an even older relic hiding beneath it, dating back to just about 1 second after the beginning, long before atoms, long before that wall of light was ever released. It's called the cosmic neutrino background, and it consists of an almost unimaginable number of neutrinos, incredibly light, famously elusive particles that decoupled from the rest of the universe's matter and radiation while everything was still almost impossibly hot and dense. Neutrinos are notoriously difficult to detect even under ideal, controlled conditions, because they interact with ordinary matter so weakly that trillions of them pass directly through your body, through the earth beneath you, through entire planets, every single second, almost never interacting with a single atom along the way. Detecting a faint, ancient background of neutrinos, stretched and cooled by billions of years of cosmic expansion until their energy is almost impossibly low, sits well beyond the reach of any instrument built so far. Physicists are confident this background exists, since it emerges naturally and reliably from the same well-tested physics that correctly predicts so much else about the early universe. But confirming it directly, catching even a handful of these ancient particles in the act, remains one of the genuine open challenges in modern cosmology. If it's ever detected directly, it would offer something the cosmic microwave background never could: a glimpse even further back into the universe's first single second of existence, a window into an era currently hidden completely from view, tucked just behind the very earliest wall of light we're already able to see. For now, it remains a background hum predicted with confidence but never quite heard, a little like knowing, with complete certainty, that a particular sound is happening somewhere in a room, long before any instrument sensitive enough to actually record it has been built. Zoom out far enough, past our galaxy, past our local cluster of galaxies, and you eventually arrive at the true address of our cosmic neighborhood, an enormous structure with a name that translates, fittingly, to immense heaven. Astronomers call it Laniakea, a name drawn from Hawaiian, chosen deliberately by the researchers who first mapped its true boundaries in 2014. It describes what's known as a supercluster, an enormous gathering of galaxy clusters and groups, all connected by mutual gravity, all drifting gently together across an almost incomprehensible span of space. Laniakea itself stretches across roughly 520 million light-years, and it contains an estimated 100,000 galaxies, including our own Milky Way, tucked quietly along one of its outer edges. Mapping something this large required an entirely different approach than simply measuring distances. Instead, the researchers tracked the actual motion of galaxies across a huge volume of space, measuring not just where each galaxy sits, but which direction it's drifting and how quickly. What emerged from that motion was something like a vast, invisible watershed, similar to the way water flowing across a landscape naturally reveals the boundary of a river basin, even without any visible line marking where one drainage area ends and another begins. Galaxies within Laniakea are all gently flowing toward a shared, gravitationally significant central region, the same Great Attractor we discussed earlier tonight, while galaxies just beyond Laniakea's boundary are found instead drifting toward entirely different superclusters, pulled by different gravitational neighborhoods altogether. There's an edge to smallness as well as an edge to vastness, and strangely enough, physicists suspect the two might eventually meet. Everything we've explored tonight has pushed outward, toward the largest distances, the oldest light, the farthest edges of the observable universe. But there's a very different kind of edge tucked at the opposite end of the scale entirely, down at distances almost too small to describe in any intuitive way. Physicists call it the Planck length, a distance roughly 100 billion times smaller than a single atom, and it's thought to represent the smallest meaningful length that has any physical significance at all. Below that scale, our current understanding of physics doesn't just become difficult. It appears to genuinely break down, the same way our equations for gravity break down at the very center of a black hole. Space and time, which behave smoothly and predictably at every scale we can currently probe directly, are thought to become something else entirely at the Planck length, no longer a smooth, continuous backdrop, but something closer to a chaotic, foaming texture, sometimes described, quite evocatively, as quantum foam, where tiny fluctuations in the fabric of space-time itself may briefly flicker in and out of existence, far too small and far too fast for any instrument to ever directly observe. What makes this genuinely fascinating, especially on a night spent discussing the largest edges imaginable, is that many physicists suspect a fully complete theory of the universe, one that successfully merges gravity with quantum mechanics, something no one has yet managed to achieve despite decades of dedicated effort, might end up describing the largest cosmic horizons and the smallest quantum scales using surprisingly similar underlying mathematics. Some approaches to quantum gravity even suggest that the total information a region of space can hold might be limited by its surface area rather than its volume, a strange, almost architectural idea, hinting that the smallest conceivable scale and the largest conceivable boundary might be two ends of the very same rope, rather than two completely separate subjects. It's a comforting kind of symmetry to end this particular thread on. The edge of the unimaginably large and the edge of the unimaginably small may not be opposites at all. They may simply be two doors into the same unfinished room, both still waiting for someone to find the key. There's a photograph taken from the very edge of our own solar system, looking backward instead of outward, that shows Earth as a single, pale, nearly invisible speck of light, smaller than a pixel, suspended in a beam of sunlight scattered across the camera's lens. It was taken in 1990 by Voyager 1, the same spacecraft we discussed earlier tonight. Its cameras turned around one final time before being shut down to conserve power for the long journey still ahead. From a distance of about 6 billion kilometers, roughly 40 times farther from the Sun than Earth itself, the camera captured our entire planet as a single point of pale blue light, a fraction of a pixel wide, easy to miss entirely if you didn't already know exactly where to look. The astronomer Carl Sagan, who had pushed for the photograph to be taken in the first place, wrote about it afterward in words that have stayed with people for decades since, describing that tiny, barely visible, at his home to everyone who has ever lived, every joy and every suffering, every civilization, every war, every quiet, ordinary evening, all of it contained within that single, nearly invisible speck of light, suspended, as he put it, on a mote of dust caught in a sunbeam. It's worth returning to that image tonight, after everything we've covered, because it offers a kind of scale that's easy to describe in numbers, but much harder to actually feel. Every fact tonight, every boundary of light, every wall of ancient radiation, every void, every supercluster, every collapsing star, exists at a distance from that single pale that's so enormous that our entire solar system, Sun included, would still appear as nothing more than a faint smudge against the true scale of the observable universe. And yet, from inside that speck, someone is lying quietly right now, in a bed, in a room, letting go of the day, listening to a voice talk about the edge of everything, while the vast, patient universe continues on entirely unaware, exactly as it always has, and exactly as it always will. There's no contradiction in that smallness. If anything, it might be the most restful thought of the whole night. You don't need to hold up any of it. You never did. It was always going to keep turning quietly on its own, whether you were awake to watch it or not. So let's return, gently, to those 3 questions from the very beginning of the night. What is the universe expanding into? Perhaps nothing, because it doesn't need an outside at all. It simply is the whole of what there is, quietly stretching within itself. Are you looking at space, or at time, when you look upward? Both, always, at once. Every point of light above you a small window into somewhere far away, and, just as truly, somewhere long ago. And is there a place out there where the rules simply stop applying? Perhaps. Or perhaps the rules never really stop. They simply become quieter, harder to hear. The further out you go, the way a voice fades not because it stops speaking, but because the distance grows too wide for the words to carry. You don't need to have answers to any of this tonight. Nobody does. Not even the people who study it for a living. That not knowing isn't a gap in the story. It might be the most honest, most peaceful part of it. You are, tonight, lying somewhere on a small world, wrapped in the same night sky that every person before you has ever wondered about, looking out at light so old it left its source before you, or your parents, or the language you're thinking in, ever existed. And still, none of that vastness asks anything of you. It doesn't need you to understand it, solve it, or stay awake for another single fact. It simply asks you, if it asks anything at all, to rest. So let your eyes stay closed a little longer now. Let the weight of the day settle out of your shoulders, out of your jaw, out of the small tension behind your eyes that's been holding on all this time without you noticing. There is nowhere else you need to travel tonight, no edge you need to reach, no boundary left to cross. Just this room, this bed, this breath, and the quiet, patient dark, holding you exactly the way it holds everything else, gently and without asking for anything back. Thank you for spending these hours here in Somniora Mind, one quiet mind at a time. Rest now. You've earned it. Good night.